Intentional stone heat treatment is a key marker for prehistoric behavioral variability. Yet the relationship between differences in heat treatment strategies and variations in stone tool-making processes remain heavily debated and poorly understood. Here we report on extracts from a series of experiments testing wood fuels and heating strategies applied to silcrete nodules from 60 kilometers south of Diepkloof rock shelter in South Africa. Fires used to systematically manipulate the natural properties of rocks was a key Stone Age behavioral innovation. South Africa's Middle Stone Age record has in recent years attracted the attention of researchers because of its rich evidence for silcrete heat treatment. Brown and colleagues were the first to argue that South African silcretes were intentionally heat treated with dates of over 160,000 years ago from Pinnacle Point. They hypothesized that prehistoric humans heat treated silcrete to increase its functional performance, and that these functional qualities drove the invention of early forms of thermal engineering. More recently, Schmidt and colleagues published the dates for heat-treated silcrete even further back in time in a paper where they compare the silcrete assemblages from two archaeological sites situated along the southwestern coast of South Africa. Their results suggest that the invention of heat treatment occurred sometime between 130 and 200 to 400,000 years ago. Wadley and colleagues and Brown and colleagues proposed that the invention of temperature-induced transformations of silcrete required the setup of a dedicated heating environment using sandbars. Wadley's experiments showed that surface-fired thin-cut silcrete slabs crack, while those heated in a sandbath remained intact. Given the early dates for heat-treated silcrete in Southern Africa, potential finding that heat treatment requires significant investment and skill would support the hypothesis that humans made key and early innovations in raw material preparation strategies that required analogical thought. However, experiments by Patrick Schmidt and colleagues show that normal surface fires can be used to successfully heat treat silcrete. Moreover, at Diepkloof rock shelter in South Africa, Schmidt and colleagues identified a black film on silcrete surfaces that contains microscopic fragments of charcoal that formed as residue during the direct contact of the artifacts with hot embers of green wood. Their results suggest that heat treatment of silcrete was conducted directly in open fires, similar to those used likely for cooking or other utilitarian purposes. But all of these studies lead to an even more fundamental question. Why was silcrete heat treated? McKay and Schmidt tackled this question, and they conclude that heat treatment may have been used to improve the fracture properties of silcrete at times when other fine-grained rocks were less readily available. However, the question remains, what were the functional benefits of heating silcrete? Willem McKay's meta-analysis of silcrete frequencies from 200 South African Stone Age assemblages shows that the silcrete abundance is significantly correlated with assemblages emphasizing the production of miniaturized tools, that is, small flakes, bladelets, and small retouch tools or microliths. We therefore have strong reasons to hypothesize that heating silcrete allowed prehistoric toolmakers to make smaller cutting implements and to more intensively reduce their cores. Recent work by Torchi links increased edge regularity at the microscale to reductions in force requirements when cutting with heat-treated flint. It is therefore likely that in addition to benefiting lithic miniaturization, silcrete heat treatment also increased flake edge sharpness. To date, however, it remains unknown whether stone tools made from heat-treated raw materials actually display sharper edges relative to unheated alternatives. Moreover, when discussing heat treatment's benefits for stone tool production, most experimental studies thus far mention the increased ability to produce larger and longer flakes using less force. These experimental designs do not line up with the archaeological data as we see it in Southern Africa, necessitating a new experimental study focused solely on lithic miniaturization. Here we report on a set of experiments that address the following research questions, the following two. Our test hypothesis is that simple surface fire heat treatment improves the nappability of silcrete nodules. Specifically, we contend that with the intended goal to miniaturize flake production and maximize core utility, unheat-treated silcrete nodules should produce on average larger flakes with duller edges than heat-treated silcrete nodules. This experiment used one large silcrete block weighing approximately 30 kilograms collected from an outcrop near the town of Hopefield in South Africa's Western Cape province. Two nodules were broken from the silcrete block. One of these was kept as an unheated control, and the other nodule was heated in an Embers cone heating condition. The wood fuel for the experiment was collected on the premises of Diepkloof farm one day before setting up the fire. For this experiment, we made use of a fire from identified wood in South Africa's Middle Stone Age record. Among these, we chose Cercia lavigata logs because there is published data on their use at Diepkloof rock shelter. We started the fire by first lighting branches with these leaves, and then when the thick white smoke disappeared, progressively adding thicker branches. Once the fire was going, we observed moisture and tree resin exuding from the woody stems. One silcrete nodule was heated within these ashen embers. We maintained the fire until a cone of embers and ashes formed below the burning branches, pushing apart the embers with a stick and then inserting the silcrete nodule. The embers were then moved to cover the silcrete block so that the block sat in the middle of the ashen embers cone. Following the heat treatment, each silcrete nodule was broken into several sub-nodules to facilitate the napping. The experiment's overall goal was to reduce the sub-nodules until accidents were insurmountable. We used a large plastic canvas sheet to cover all chips, chunks, and flakes after napping. Using a random number generator, we then selected 100 flakes from each of the flake debris bags. The total sample amounted to 1,000 flakes. We tracked 3 variables to determine differences in silcrete utility before and after heat treatment. First, we calculated an index of utility for each flake by dividing each flake's cutting edge length by its mass cubed. We tracked reduction intensity by weighing each core before and after napping. And last, we investigated the sharpness of unheated and heated flakes edges using an Instron universal testing machine and a standardized hafting protocol. For the sharpness test, I selected 30 flakes from each heat treatment condition. These flakes were then sent to Alistair Key, who was kept blind as to each flake's heating condition. We attempted the control for edge angle at this initial flake selection stage by selecting flakes with edges of around 30 degrees. Subsequently, Alistair identified the most homogeneous 10 millimeters of length for each cutting edge for use in the controlled cutting tasks. These tests involved measuring the force, work, and displacement necessary to cut a PVC pipe using hafted, heated, and unheated silcrete flakes. Now for the study results. The results you're about to see are hot off the press in 2 papers published with the Journal of Archaeological Science Reports, and a second upcoming in the journal Archaeometry. Our first results showed that surface fire heated silcrete produced a significantly higher amount of flake cutting edge to mass on flakes compared to unheated silcrete. Our second results showed that surface fire heat treated cores are significantly smaller and offer greater utility on average than unheated cores. Our sharpness tests show significant differences between the heated and unheated silcrete flakes in terms of the force, work, and displacement when slicing through the PVC tube. When flakes are fresh and at their sharpest, heat-treated flakes require roughly half as much force and about 1/3 the energy to cut through the PVC tube. Importantly, our experiments also showed a black tempering residue on the surface of all the heated samples. These residues resemble those found on the surface of archaeological silcrete flakes from Dipcliff rock shelter, supporting the hypothesis that they were also heated using surface fires. Our experimental results demonstrate that simple surface fire heat treatment significantly improves the nappability and functional qualities of silcrete nodules and flakes. Smaller flakes provide several obvious advantages over larger flakes in terms of reduction efficiency. These economic benefits would have direct payoffs in environments where suitable raw materials were scarce. Archaeological data on South Africa's silcrete procurement patterns shows prehistoric toolmakers preferentially selected for silcrete when miniaturizing lithic production. Our experimental results explain why they did this. We argue that heat treatment energy requirements would have decreased considerably, potentially outweighing the costs associated with making and maintaining a fire, given that multiple silcrete nodules, capable of producing numerous tools, could be heated simultaneously. When the necessity of fire for heating, cooking, and safety are also considered, there was likely little energetic cost to engineering silcrete in this way, relative to the substantial benefits. Together, these selective pressures could have provided a strong mechanism favoring the widespread use of heat-treated silcrete. Lastly, our results support the hypothesis that temperature-induced transformations of silcrete did not require the setup of a dedicated heating environment using sandbaths, and may have been performed in the same context as other fire-related activities. We argued that rapidly heating silcrete for stone tool production was efficient at relatively lower levels of investment in skill learning and analogical reasoning than currently thought. Thank you very much, and I appreciate your attention.